Before we move into the analysis and control of dynamic systems, we need a few basic ideas in place: functions, equations, derivatives, and ODEs and PDEs. This video is a quick conceptual reminder of the notation we'll use later. If you don't feel comfortable with any of these ideas yet, I'd strongly recommend revisiting them before moving on. Let's start with functions. A function describes how quantities depend on one another. In mathematics, we call these quantities variables. If you write y equals f of x, we are saying that x is the input, f is the rule or relationship, and y is the output. So, in this example, y depends on x. In many contexts, this idea is very useful. Position might depend on time, temperature might depend on position, and voltage might depend on current. The names of the variables do not determine their relationship. We have to look at how the variables are connected. So, when reading a function, the useful question is, what depends on what? Next, let's talk about equations. An equation is a statement that two expressions are equal. Sometimes we use an equation to solve for an unknown value. For example, if we have 3x plus 2 equals 8, then we can solve for x and get x equals 2. But equations are not only used to find numbers. They can also describe relationships. For example, y equals 3x squared describes how y is related to x. This distinction matters because when we get to differential equations, we are usually not just solving for one number. We are describing a relationship involving a function and its derivatives. Next, we need the idea of a derivative. If we have a function, y equals f of x, then the derivative tells us how y changes when x changes. We write this as dy by dx. Conceptually, it is the change in y divided by the change in x, in the limiting sense. So, the derivative compares how much the output changes to how much the input changes. If a small change in x causes a large change in y, the rate of change is large. If a large change in x only causes a small change in y, the rate of change is small. A common interpretation is that the derivative is the slope of a graph. That is useful, but the broader idea is rate of change. For example, if x is position and it depends on time, then dx by dt is velocity. The second derivative, d squared x by dt squared, is acceleration. So, derivatives are not just abstract notation. They often represent physical rates of change. Now, we can put the previous ideas together. A differential equation is an equation that relates a function to one or more of its derivatives. In ordinary algebra, we often solve for a number. With differential equations, we're often solving for a whole function, such as y of x or x of t. So, a differential equation combines the ideas of functions, derivatives, and equations. For example, dy by dx equals 3x squared is a differential equation because it relates the function y of x to its derivative with respect to x. The second example is the equation for a simple mass spring damper system. It looks more complicated, but the idea is the same. The function is x of t, and the equation contains both the first derivative and the second derivative of x with respect to time. This kind of equation is important for dynamic systems because it describes how a quantity evolves over time. Now, let's make the idea of dependence more explicit. If we write x of t, we are saying that x depends on t. Here, t is the independent variable. It is the variable we use as the reference. In the dynamic systems we will focus on, this is usually time. The dependent variable is the quantity that changes in response. In this example, that is x. It might represent position, displacement, angle, voltage, or some other system variable. So, before working with a differential equation, it is useful to ask, what are the dependent variables and what are the independent variables? In other words, what depends on what? An ordinary differential equation, or ODE, involves derivatives with respect to one independent variable. If the function is x of t, then the derivatives are ordinary derivatives, such as dx by dt and d squared x by dt squared. The order of an ODE is the highest derivative that appears. So, an equation involving only the first derivative is first order, while an equation involving the second derivative is second order. The mass spring damper equation we saw earlier is an ODE because all the derivatives are with respect to the same independent variable, t. It is a second order ODE because the highest derivative is the second derivative. ODEs are especially important in dynamic systems because they describe how quantities change with respect to one independent variable, often time. We can also have systems of ODEs where several dependent variables are connected through several equations. But for now, the key idea is still the same. The derivatives are taken with respect to one independent variable. A partial differential equation, or PDE, appears when the function depends on more than one independent variable. For example, the temperature in a metal rod might depend on both position and time. We could write this as capital T of x and t, where x represents position and t represents time. Because the function depends on more than one independent variable, we use partial derivatives. A partial derivative tells us how the function changes with respect to one variable while holding the other independent variables fixed. So, the partial derivative of capital T with respect to t describes how temperature changes with time at a fixed position. The partial derivative of capital T with respect to x describes how temperature changes with position at a fixed time. The equation shown here is an example of a PDE because the function depends on more than one independent variable and the equation contains partial derivatives. Before we finish, it is useful to note that the same derivative can be written in different ways. The notation dx by dt is called Leibniz notation. It makes the independent variable explicit because we can see that the derivative is with respect to t. In dynamics and control, we also often use Newton notation. Here, x dot means the first derivative of x with respect to time. Similarly, x double dot means the second derivative of x with respect to time. You may also see prime notation, such as y prime. This is compact, but the independent variable is not shown directly, so its meaning depends on context. The main thing to remember is that the dots usually mean derivatives with respect to time, while Leibniz notation makes the independent variable explicit. To recap, before working with a differential equation, it helps to slow down and make sense of the notation. Ask what quantity is changing, what it is changing with respect to, and what derivatives appear. Once you know what the quantity depends on, the distinction between ODEs and PDEs becomes much clearer. One independent variable means an ODE, while more than one independent variable means a PDE. The main habit is to understand what the equation is telling you before trying to solve it. That gives us the foundation we need for working with dynamic systems later.